So in this video we're going to cover section 7.4, which are sample size considerations. What the overarching picture of this section is this. So far what we've always done is, if we were looking to estimate the population mean, we always started off our questions with determining whether or not our sample size was large, so greater than or equal to 30, and also whether or not our population standard deviation sigma was known. Whenever we look to estimate the population proportion, we always also wanted to determine whether or not our sample size was large, but we went about that a little bit differently in the last section. But in either case, whether we're estimating the population mean or the population proportion, we always wanted to see whether or not the sample size that we had was large. What we're going to do in this section is we're going to go in the opposite direction. We're going to say, hey, suppose that we want to say something about those parameters, and we want to have a certain level of confidence in the estimate that we're making, and also we want to have our margin of error to only be a certain size. How big does our sample size need to be in order to make those things happen? So what we're doing now instead is this. Instead of being given a sample size and then determining our confidence interval, what we're doing is we're saying, hey, if we want our confidence interval to look like this, how big does our sample size need to be? So that's what we're going to do right here. We're going to figure out the minimum sample size that we need in order to come up with a certain confidence interval. And what we're going to be doing here is we're going to first look at the mean, and then down here you can see that we're also going to do the same thing for the population proportion. So let's start off with the mean. It says the estimated minimum sample size n needed to estimate a population mean mu to within e units, or a margin of error at a certain confidence level, is given by this formula right here. So this formula right here is really important. So basically what it's saying is, if you want to figure out what your sample size is, which is again little n, we're going to take our z sub alpha divided by 2 value, and by now we should all feel comfortable about how to figure out z sub alpha divided by 2's, and square it, and then times sigma squared, so we're going to assume that we know sigma, and also here our margin of error squared. So what we need to do then, in order to find little n, is we need to know these three values: z sub alpha divided by 2, sigma, and our margin of error e. So we need to know these three things. So our problems are always going to give us these three things, and then it's going to tell us to determine what our sample size is. And this formula right here is really just a manipulation of the formulas that we were using before in the previous sections. Just did a little bit of algebra to that previous formula to solve for n, but this right here is really nothing new. Now, keep in mind that the way that this formula right here is written is this. We have z sub alpha divided by 2, so I'm really just copying this formula over here one more time. So what I just wrote down is really nothing different than what we have right here. But keep in mind that we can also write this as, since these two things are getting multiplied together in the numerator, and this is the only thing that we have in the denominator, algebraically we could also write this as z sub alpha divided by 2 times sigma divided by e, and then this whole quantity squared. So just keep in mind that we could be doing these things this way or this way using either one of these two formulas. These two formulas are algebraically equivalent. In some textbooks you'll see it written like this. In the textbook that we're using, we see it mostly like this. I'm going to pretty much just use this left-hand formula over here, but just keep in mind if you see it like this somewhere else, that it's just saying the exact same thing. Alright, so let's do some examples with this. It says this is a minimum sample size for the population mean example. An economist wishes to estimate with a 95% confidence interval the yearly income of welders to within $1,000. She estimates that the range of income is no more than $24,000. So using the empirical rule, she estimates that the population standard deviation to be about 1/6 as much, or about $4,000. Find the estimated minimum sample size required. Alright, so again, we can start this problem off the same way that we were starting off the previous examples that we were doing. And that is, how do we know that this is a Chapter 7 question? Well, we know that this is a Chapter 7 question because it's talking about a confidence interval. And we said that confidence intervals are always going to come from Chapter 7. So the way that we were doing this before was if we were dealing with the mean, which we are here, it's telling us that it's a population mean example, we always started off with the two questions, is n greater than or equal to 30 and is sigma known? But now we're going to do this slightly different. And the reason why we're going to start this problem off slightly different is because it's asking us to estimate the minimum sample size. So this is a slightly different Chapter 7 type question in the fact that it's asking us to estimate the sample size. So whenever it asks us to estimate the sample size, we're going to instead start off with this formula, again, as long as we're dealing with the mean. So here, we're going to start off with the formula of n is equal to z sub alpha divided by 2 quantity squared times sigma squared divided by e squared. So if we can figure out what these values are and plug them into this formula, then it's just arithmetic, so we can then figure out what little n is. So let's see if we can do this here. Let's start off with the z sub alpha divided by 2 value. We have a 95% confidence. We're trying to construct a 95% confidence interval. So therefore, we have a 95% confidence level. If we have a 95% confidence level, then we know that alpha is equal to 5%, and alpha divided by 2 is equal to 2.5%, or 0.025. So therefore, the z value that corresponds to 0.025 in that left tail is equal to 1.96. And I'm hoping that everybody is starting to feel pretty confident with looking up those z sub alpha divided by 2 values. If how we got 1.96 is a little bit shaky to you, go back and watch some of the previous lecture videos for Chapter 7 because we go over that in detail. Particularly look at the first lecture video where we did a couple of examples right at the beginning of this chapter. So here for z sub alpha divided by 2, we have 1.96. Next value that we need to figure out is sigma. So let's see where in this problem does it tell us what sigma is. Again, sigma is our population standard deviation. So here it tells us that our population standard deviation to be about 1/6 or 4,000. So therefore, we're going to use sigma to be 4,000. Now, some of you might be wondering where this $24,000 comes into effect. And basically what it's saying here is this. I'm going to do a really quick aside just to try to clarify this sentence right here, because they used this in a previous final exam. And I wouldn't be surprised if they had something similar in a future final exam, maybe even one for this semester. Or maybe it's going to be on your in-class exam or on your homework. But basically what it's saying here is this. It's saying that the range of incomes is $24,000. Now remember that the range is defined as the maximum value minus the minimum value. So whatever the maximum value is, if you subtract the minimum value from it, it's going to say that the range is equal to $24,000. So we don't know what the maximum value is, and we don't know what the minimum value is, but what we do know is that from the maximum to the minimum, it's $24,000. So remember what the empirical rule says, right? Here they're talking about the empirical rule. What does the empirical rule say? Remember that the empirical rule, there's primarily 3 percentages to always remember for the empirical rule. And what are those 3 percentages? 68, 95, and 99.7%. So that means that if we go from the mean, right, assuming that we have salaries or yearly incomes that are normally distributed, then 99.7% of those salaries are going to be within 3 standard deviations above the mean and 3 standard deviations below the mean. So if we go 3 standard deviations above the mean and 3 standard deviations below the mean, we're going to have approximately 99.7% of the salaries within that range. Well, 99.7% of the salaries is pretty darn close to all of the salaries. So therefore, if all of the salaries, right, approximately all of the salaries are 3 standard deviations above the mean to 3 standard deviations below the mean, and we know that that constitutes $24,000, right, from the highest to the lowest salary is $24,000, then we can divide this 24,000 by 6, right? Because we have 1, 2, 3, 4, 5, 6 standard deviations. And if you divide 24,000 by 6, this is equal to $4,000. So then we can say each one of these standard deviations is equal to $4,000. So that's what they're doing right here in this sentence. But basically, all that we need to know for our formula is how big is sigma, and it breaks it down to us right here that it's $4,000. But keep in mind, if they didn't tell you that it was $4,000, if they just told you that it was normally distributed, right, that the salaries are normally distributed, and that the range is $24,000, you can estimate that the population standard deviation sigma is about $4,000. All right. The last thing that we need to know is capital E, which again stands for our margin of error. Whenever we're trying to figure out what our margin of error, we're trying to figure out our wiggle room. And our wiggle room here, it says that this economist is wishing to estimate the yearly income of the welders to within $1,000. So plus or minus $1,000. So therefore, the wiggle room that we're giving ourselves is $1,000. So we can put in 1,000 for E. Now, a quick way to figure out what our margin of error is, and I think I might have said this in a previous lecture video, is whenever you spot the word within, right after that usually follows what your margin of error E is going to be. So if you're running short on time on an exam or something like that, and you're trying to quickly locate what our margin of error E is, if you can figure out where it says within and the number that comes after within, that's usually a pretty darn good bet that is talking about your margin of error E. Alright, well now we have it. We have all of these numbers right here. If we do the arithmetic on this, then it's going to come out to 61.47. Alright, so let's think about this here. She's trying to figure out the average yearly income of welders. And this economist is trying to figure out how many welders does she need to ask what their yearly income is in order to come up with an estimate to within $1,000 of, on average, how much do welders make. So what we just determined is that she needs to ask a minimum, right? We're talking about the minimum sample size. We're estimating the minimum sample size. We're saying that she needs to ask a minimum of 61.47 welders. So she can't ask 61 welders, because then she wouldn't have gotten to the minimum of 61.47 welders. So therefore, what we have to do is, we have to round up to 62 welders. So, therefore, regardless of what the decimal place is, we always round up, because we're talking about a minimum. Even if, right, so hypothetically speaking, had we had slightly different numbers, even if we would have calculated out 61.0001, if the minimum threshold that you need to meet is 61.00001, I added an extra O there when I said that, so I'll scribble in that extra O. If this is the minimum threshold that you need to meet, doing 61 is not good enough. So therefore, regardless of what the decimal place is, you always round up. So whenever we're calculating out the minimum sample size, we always round up. So that's how we got to our final answer, that our minimum sample size is 62. Alright, so let's go on to the minimum sample size for the estimation of a population proportion. So now we're going to go away from the means and we're going to talk about the population proportion. And what we're going to do here is mostly the same thing, but slightly different. So again, we're trying to figure out what little n is, our minimum sample size. But this is whenever we're dealing with our population proportion P instead of with our population mean mu. And if you compare this formula right here to the one that we were using above, that I put in a box, so if you try to compare this box up here to this box right here, you can see that it's mostly the same. What we have here is this. The only thing that's different in this formula is that we're replacing sigma with p hat times 1 minus p hat. So here the only thing that's different is that we're replacing sigma squared with p hat times 1 minus p hat. And remember that p hat stands for our sample proportion. Alright, so here's this. There could be a situation where the problem tells us what p hat is, but there could also be a situation where the problem does not tell us what p hat is. If it tells us what p hat is, or some estimate for p hat, well, then we can just plug that number into the formula and we're good to go. But if it does not tell us what p hat is, then our default for p hat is that we're going to use 0.5 for p hat. And 0.5 for p hat is what's known as the most conservative estimate. And why it's the most conservative estimate is going to be a little bit easier explained after we do these next two examples. So let's first do these next two examples, and after we do these next two examples, we'll backtrack, and then we'll see why p hat being equal to 0.5 is known as the most conservative estimate. So let's do it. this is a minimum sample size for the population proportion, or this is an example of that. It says for number 1, find the necessary minimum sample size to construct a 98% confidence interval for P with a margin of error of E is equal to 0.05, assuming that no prior knowledge about P is available. Alright, so let's do it. Just like I have been doing for this entire chapter, I'm going to first ask you the question of, how do we know that this is a Chapter 7 question? And we know that this is a Chapter 7 question because it's talking about confidence intervals. But what we're trying to do now is we're trying to calculate out the minimum sample size. So here I put a squiggly line under necessary, left off size. So here, let me fix that. Trying to figure out the minimum sample size. So instead of starting off with asking, is our sample size large enough? We don't know our sample size. We're trying to figure that out. So therefore, we know that we're going to try to calculate out little n. Here we're dealing with the proportion P, so we know that the formula that we're going to use is Z sub alpha divided by 2 quantity squared times P hat times 1 minus P hat over E squared. And if we could plug numbers into this formula for Z sub alpha divided by 2 E and P hats, we'd be good to go. So let's see if we can do it. First off, we have a 98% confidence interval. That's what we're trying to construct. So therefore, how big is alpha? Alpha is equal to 2%. So therefore, alpha divided by 2 is 1%. So let's try to figure out the Z sub alpha divided by 2 value for 1%. So we're going to use our t-table to do that, just to jog our memories about the t-table. And our alpha divided by 2 value, right, so we have Z sub alpha divided by 2. Our alpha divided by 2 value, we're saying is equal to 1% or 0.01. So therefore, we're going to come over here to the 0.01 column. Now, all of these values right here are t values, except when we go to the back side of our t-table and we follow this column, right, the 0.01 column, we follow it all the way down to the bottom. And again, remember that this very last row right here are z values. And that's what we're trying to figure out. We're trying to figure out z sub alpha divided by 2. So again, if we go into this column, we get that z value to 3 decimal places, which is why we're using the t-table instead of the z-table, because if we use the z-table, we'd get down to 2 decimal places, or we could approximate that 3rd decimal place. But here we can get exactly what that 3rd decimal place is. So 2.326 is what we're going to be using for this z sub alpha divided by 2. And our margin of error, it literally tells us that E is equal to 0.05 right here. So I can plug that in. But now what do we use for P hat? It doesn't tell us what P hat, right? And remember that P hat is our sample proportion. And we always use our sample proportion to estimate what our population proportion is. We use our sample information to estimate some characteristic about the population. Or another way of saying that is we use our sample statistics in order to estimate our population parameters. So therefore, here it's telling us that we have no prior information about what our population parameter P could be, our population proportion P. So therefore, we don't have an estimate of what P is, or we don't know what P hat is. And whenever we don't know what P hat is, we're saying that we're going to use P hat to be equal to 0.5. So therefore, I'm going to plug in 0.5 and 1 minus 0.5 for p hat in these two spots right here. And if you do this arithmetic is going to come out to 541.03. Now, is that our final answer for A? And the answer to that is no, because remember what we said, that no matter what the decimal place is, we're always going to round up. So therefore, the next highest whole number is 542. So therefore, our final answer for A is going to be that our sample size, our minimum sample size, is going to be 542. Alright, the only time that you don't have to round up is if the numbers just happen to so work out that you end at exactly a whole number. So suppose that we didn't come up with 541.03. Suppose that we stopped at exactly 541. Well, if we land at exactly a whole number, you don't have to round up because we're already at a whole number. The only thing that we want to do is always land at a whole number. So since here we were just a little bit off of our whole number, we're always going to round up to the next highest whole number. Alright, let's do B. Now it's saying that we still want to do this, but now we're assuming that a prior study suggests that P is about 0.1. So since we're still trying to calculate out the minimum sample size needed to estimate the population proportion, we're still going to start off with this formula. We still have the same confidence level, so therefore we're still going to use 2.326. We still have the same margin of error, so we're still going to use 0.05. Obviously, both of those quantities are squared. But now it's telling us that an estimate for P is 0.1. So a previous study indicated that an estimate for P is 0.1. So therefore, we can use that for P hat. So 0.1 times 1 minus 0.1 right here. And if you do this arithmetic will come out to 194.77. Again, is this our final answer? No, because we have to round up. So therefore, our final answer is going to be that it comes out to 195. Because we want to round up to the next highest whole number. So let's take a look at these two numbers. If we had some estimate for what P hat is, here just happened to be 0.1, the minimum sample size that we needed was 195. However, when we said we didn't have a P hat estimate, we would use 0.5, and then the minimum sample size that we needed was 542. Clearly, this sample size for part A is much, 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 much larger than the sample size for part B. So let's think about this here for a second. If we're trying to figure out a confidence interval, somebody says, hey, I want to figure out this confidence interval. How many people do I need to have in my sample to come up with this confidence interval? First, your reaction probably is, well, I don't know. So they're saying, all right, well, I just want to know the minimum amount of people that I need to go out and ask. Well, if you want to make sure that they go out and ask the right number of people, you're going to say, hey, I'm going to come up with a conservative estimate so that we don't fall short of our objective. So I'm going to give you a high number to make sure that we make sure that we ask the right number of people so we can come up with this estimate. So that's why you're going to say, go out and ask a whole lot of people. And even if you ask too many people, at least then we know that we're going to be able to still do what we want to do. If we fall short of having the right sample size in order to come up with this confidence interval, all that we're going to have to do is go out and ask more people in order to get our sample size large enough. So if you want to make sure that on the first try you ask the right amount of people, you better go out and ask more people in order to get, in order to be able to achieve your objective, right? Think about it like this. If you want to figure out the average height of students at UNCC, going out and asking one person is probably going to be an insufficient sample size to figure out what the average height is of all students at UNCC. Asking 5 people probably wouldn't do it. Asking 10 people probably wouldn't do it. You're going to probably have to ask something like, 300-400 people what their height is in order to come up with a pretty accurate estimate of what the average height is of students at UNCC. So if somebody comes up to you and says, how many people do I need to ask what their height is? You're going to say, I don't know. But you probably want to ask a couple of hundred people just to make sure that you can come up with an accurate estimate. And if they say, what's a couple hundred people? Say, I don't know. But ask 600 or 700 people, and then you're going to probably be good to go. So you're going to err on having a large sample size versus a small sample size, right? You're not going to say to this person, ask 2 people and you should be good to go, right? Mathematically speaking, what we're doing here is this. If you just look at how do we get this number right here to be large, right? If that intuition that having a large number now makes sense, if we want this number right here to be large, and if you look at this formula right here, our denominators were the same, the only way that we can get this number to be large, then, is if our numerator increases. The only thing that we're changing then is this product. The product between these two things. Now, how do we get this product to be our largest? Well, what we did down here was we used 0.1 times 1 minus 0.1, which is 0.9. This is going to be smaller than if we use 0.2 times 1 minus 0.2 or 0.8. Right here, this comes out to 0.09. This comes out to 0.16. 0.3 times 0.7 comes out to 0.21. If we plug in these values here, now our numerator is getting bigger. Well, 0.4 times 0.6 is 0.24. 0.5 times 0.5 is equal to 0.25. Now, if we go to 0.6 times 0.4, this is just the exact same thing as what we have right here. So therefore, this is again going to be 0.24. So now we're going to start decreasing again, right? So here you could do 0.3 times 0.7 and so on and so forth. So this is then going to come out to, right, I'll just write it down, 0.7 times 0.3. It's going to come out to 0.21. So you can see right here that the highest value that we're going to ever get is 0.5 times 0.5. So therefore, the highest our numerator is ever going to get is if we use 0.5 for p hat. So therefore, I'm hoping that it makes a little bit of sense now that p hat being equal to 0.5 is going to give us our most conservative estimate, which is just the highest n value that we could possibly get. Alright, and we'll leave it there for that. That was a little bit of a theoretical aside, right? Basically what we're doing here is you can also think about, you might see this in a geometry class or in a pre-calculus class or a college algebra class, where the largest area that we're ever going to get is if it's a square, so then one side is going to be the same size as the other side. Rectangles are going to always have smaller areas than squares will have, as long as the circumference of those things are the same. So these, we're getting into a little bit of a mathematical, theoretical aside here, but as long as you're good to go with the fact that if we don't know p hat, we're going to use 0.5, and that's what's called the most conservative estimate, then you should be good to go with finding the minimum sample size requirement. Alright, and that ends this section, so therefore that also ends chapter 7 and also this lecture video.